Now, my first slide has a replica of the first transistor invented at Bell Labs. And my work is looking at new materials for transistors. Now, the first transistor was reportedly dipped into a bucket of water by its inventors to show a large gain in transistor performance. And my work runs really along a similar vein. Following the invention more than 50 years ago, transistors have really become the basis of current semiconductor technology. Today, the whole industry is worth more than $300 billion and set to only get bigger. So how do they work? Well, transistors harness the electronic properties at the interface between two materials, an insulator and a semiconductor, and use this control to switch electrical currents on or off. They do this by charging up the semiconductor surface and sort of switch electrical currents on or off using a gate dielectric. Now, these gate dielectrics are limited. They can break down at high voltages, sometimes in spectacular fashion, as shown in this picture here. And we are looking at new materials that can be used as a gate dielectric, for example, an electrolyte as a gate. These type of gate materials contain many ions that can be directed to move in response to a voltage. And these allow you to achieve very high charging densities in transistors, sufficiently high to change the conductivity in even metals. Now, so far, there are two operating regimes that have been identified in devices. The ions can either sit directly on top of your semiconductor, or they can make their way into your semiconductor. Either way, both types of operating regime are useful. Now, in my lab in Cambridge, we have been looking at really demonstrating the electrolyte gating technique by building transistors using new materials. And the equipment we have allow us to measure the magnetic, electrical, and optical properties of devices, which all are useful. Now, devices are typically made by depositing a metal pattern on top of a semiconducting film grown onto a suitable substrate. We then follow this up by depositing our electrolyte gate on there, and we do careful measurements to avoid parasitic resistances and capacitances. Now, early work has focused on use of the electrolyte gate for manganites and cuprates, a class of materials that are known to show remarkable changes in electronic and magnetic properties. Here's a picture of a hard drive which really makes use of control of a magnetic property. And this has really shown that we can really change the temperature at which exotic properties in these materials tend to occur. And we can start thinking about control of properties such as magnetic levitation using this technique. So there's really a wide scope for the application of the gating technique. Now, what sort of materials do we use? They're sort of shown here. We can usually choose materials which are compatible with the electrolyte gate, and the gate itself, it can be applied by solution or deposited directly on top of your semiconductor. A useful observation from many experiments is that the shape of the drop on the semiconductor can tell you something about the operation of the device. So the hydrophilic interaction in this device is important. Now, so far, the gating material has shown very promising results. For many of the materials, however, the conventional techniques, such as chemical doping, are almost equally relevant. However, there are many materials of potential interest which can which would be really useful to gate. And we can start really thinking about sort of creating new electronic systems by bringing together different materials with different electronic properties. And for many materials, the properties at the surface can vary very much differently compared to the bulk. And if we can sufficiently sort of address these, we can think about possibly new states of matter. So what we really here have is a powerful toolkit in the form of the electrolyte gating technique, which allows us to tweak existing properties or even completely transform them. Now, for the future, we can think of transistors or electronic structures that transform from a metal or superconductor to an insulator at the flick of a switch. And this has potential applications for ideas like logic circuits, which you can define anywhere and without ever visiting a factory again. And this work also has applications in the area of batteries. Batteries are limited by their durability and capacity. However, if we extend the electrolytic gating technique to chemical structures which can support ions in the support ions inside them, we can start looking at improving energy storage devices. We also have applications in sensors. Most sensors rely on chemical detection of chemical reactions that occur at the interface between an electrolyte and a metal. However, very little work has been looked at the control of these chemical reactions using a gate voltage in a transistor configuration. And finally, two-dimensional materials such as graphene have a unique chemical structure which, if properly addressed, we can maybe access exotic electronic regimes or even build completely new structures that exploit the potential control at the 2D conducting sheet. So really, to summarize, electrolytic gating has implications beyond transistors to sensors and batteries and has the potential to create a completely new field. So I want to thank the people listed here who I've collaborations with, and I thank you for listening. Thank you.
Thanks for that. I don't know a huge amount about the field, but my understanding was that electrolytes have a problem of being relatively slow. Is that an issue
yes.
in the devices you're talking about?
Yes, that's a good point. So the ions are, I mean, the switching using the ion will be slow. However, the work done so far suggests that they're not going to be as slow as most people thought. You have reports of transistors being switched at up to megahertz speeds, which can also be useful. And it's something that if we can properly address, maybe even improve the switching frequency, if we can start thinking about how are the ions moving inside the electrolyte and how we can facilitate that motion. So it's something that is definitely an area that deserves more attention. Yeah.
So you alluded to studies of the superconducting transition that can be studied by changing by extreme doping with electrolytic gates. Is that something that you're doing in your group, and maybe can you say a few words about that?
Yes, yes. So so what we've looked at are materials that show a loss in resistance as you cool them down, and by using the electrolyte gating technique, we can change the temperature at which they lose this resistance. Now, most of the materials so far we've looked at have already been studying using conventional doping techniques. And so these high temperature superconductors work at sort of 134 Kelvin, maybe a record temperature. But if we really think out of the box and look at possible materials for superconductivity, using the electrolyte gating technique, you can really really start thinking about possibly going even higher in temperature to higher, maybe, yeah, even higher. So this is something that's really requires a sort of a broad effort, sort of from collaborations with material science and chemists who have materials which might show interesting properties if you can just charge them up sufficiently.